Hey Honors Physics, this is Mr. Hausman, and we're going to take a look at a combination circuit problem, and we're going to kind of talk out the methods or the steps that you would take to analyze the circuit. And when we say analyze, we mean we're going to find all of the features, all of the characteristics. That means we're going to find the total resistance of the circuit, and we're going to do that first. We're going to find the total current, and we're going to find out where that is happening and what that means. And then for each individual resistor, R1, 2, 3, and 4, we're going to calculate how much voltage is lost, or the potential difference at each resistor, and how much current is flowing through each resistor. So let's begin. So as we said, we would start with R equivalent. But before you kind of just jump right in, you have to kind of think about the method that was already introduced, called the inside-outside method. So if I kind of narrow my focus on the smallest inside part, I see a parallel circuit. And then wider than that is a series circuit, but the entire circuit itself at the very most outer point is parallel. So I'm literally going to have to do 3 different steps to find the resistance total, or the equivalent resistance for this whole circuit. So the first thing I'm going to do is I am going to take and do R parallel of the innermost circuit. So that's R1 to the negative 1 plus R2 to the negative 1. We can plug in there 48 plus 16, of course, to the negative 1. And I made a mistake here. We need to take the reciprocal of all of that. So you go over to your calculator, use the x to the negative 1 button, and you're going to get a 12 ohm resistance for the parallel portion that is made of the 48 and the 16. The next step is to go a little bit broader. That was R series. And the formula for that is, R12 plus the 4 ohm resistor, R2. Let's make an upside down ohm. And we get for that 16. Certainly adding resistors in series much simpler. And then we're going to do it one more time, R parallel. Now we're going to take the series circuit of the upper branch, if you know what I mean by that, right? Everything at the top is a series circuit. So we're going to take that to the negative 1 plus the R1 to the negative 1. I just noticed a mistake, just mentioning that the original 2 resistors I added were really 3 and 4. So you'll notice that I did a little fixing there in my recording. So now we have 16 plus to the negative 1 power plus 32 to the negative 1 power. Take the reciprocal of all of that. And this circuit comes out to have a, it's nice if it's a whole number. It's not the way it always works. The resistance equivalent for the whole thing is 10.67 or 10 2/3 ohms. So we'll put that in our first box. Now you might be wondering, how do I explain that? Once you become proficient at this, you just kind of know what you're doing. So really what you're doing is you're going the inside, right, or innermost parallel, added, and then the R3 plus R4 total is now added to the R2. And so that's a series addition. And then finally, R parallel addition. And someone said, you might wonder, what did he mean when Mr. Hausman asked, could we do it in a way that's a little less dry or a little bit more funny or kind of just more concise? And I suggested that you could use maybe kind of hashtag, and it's, added up, parallel, series, parallel, and you kind of have shortened or summarized what you did there, okay? So I guess that's step 1, but really that's many steps together. We're going to go on to step 2, which is to find I of the battery, or the total current, equals V over R. So we know the total voltage, and we know now the equivalent resistance. So all we need to do now here is plug in our 8 volts over our 10.67 ohms. And we get I equal to 0.749 or 0.750 amperes. If you use your 10.666 replating or 10 and 2/3, that's when you get exactly 0.75. Otherwise, it's very close, 0.7497, etc. So that's the difference. And for a reason why, right, we are using Ohm's law for, right, the whole circuit. Okay. So the catch here is, I guess, writing with this stylus on the screen, I write a little big, and so I need a little more room. So I'm now going to be able to scroll and move all my work kind of over to the side, and I'm going to continue in a new column here, right? So I'm going to look over here, and we're going to create, we're going to do work, and we're going to do the explanation, and we'll make it 2 columns. So a little continuation. Okay. So this is where a lot of students notoriously have gotten stuck. They can get the first table done. They've got the resistance patterns down, series and parallel. They have the Ohm's law formula right here. Now, where do you go? Well, the most common thing I do is I put in my current, I label it, where is the 0.75 amps? And since it's the current for the total circuit, it's 0.75 amps coming out of the battery, or closest to the battery, and it's also 0.75 amps on its return. Remember, current doesn't change in a circuit. The voltage is what drops off. Now, I'm going to get rid of these brackets from before, because that was really just a way of thinking that helped organize my resistance addition. And now what I'm going to do is I'm also going to use the color coding technique. So rather than memorizing a bunch of steps for how to analyze circuits, what you're going to find yourself doing is kind of using all of these skills that we've used on simpler circuits, okay? So what I'm doing now is showing all of the places that would be high voltage from the positive terminal, and we could even label that, if you want, 8 volts, right? This entire side is 8 volts. This entire side over here, the side connected to the negative terminal of the battery, is 0 volts. Okay. And what that just did, if you notice on the middle path, or the lower of the 2 paths, right, is you now have a delineation. You know something about the first resistor. So it kind of shows you what to do next. So we're going to go here, and we're going to fill in what we know. We just deduced, using the color code system, the voltage system, that the voltage drop there must be 8 volts. And we know that because, right, it goes from high, red, to blue, 0, 8 to 0. Then what we do is we do Ohm's law. I equals V over R. And we said we were going to do that over here. We were going to do R, oops, let's make it a color we can see, R1. And we were going to do I equals V over R. And the current through resistor 1 has to be the voltage drop, 8 volts over 32 ohms. And of course, that comes out to be 0.25 amps. So we put that in the table. And for a reason, right? Hashtag Ohm's law at resistor 1. Right? That's kind of what we're doing. Ohm's law works for the whole circuit, or anytime you have a voltage, a resistance, and you're trying to find an unknown current for an individual component. Okay, so again, a lot of people They're like, okay, so I can't tell what the voltage drop is for R2, 3, or 4 because together they have to add up to 8 volts. So what you're going to find yourself doing is when you don't know exactly kind of where to go next, you take whatever you just calculated and you ask yourself kind of like, put that in. Put that into the picture. Put current into my diagram and use the little dot again. Remember these little dots that remind you how much current is flowing? So I just deduced or calculated that 0.25 amps of current have to be flowing through this bottom pathway. There's a top and a kind of a middle, if you will, or bottom. And so what you notice is that a quarter of your current, you only have 3/4 to begin with, 0.75, and 1/4 goes this way. So what you can deduce is, and let's use another color, is that the I total must be the sum of the two currents, because there's really a top path and a bottom path. So if we know the total current is 0.75 amps, and the bottom path we just figured out is 0.25 amps, well, I2 is clearly 0.5 amps. And where that goes to, ironically, literally, is that goes up here to this pathway, 0.5 amperes, and it gives us a hint now about R2. But we don't know its voltage. We're actually going to put in its current. So there's this little pattern, I call it. It's kind of like playing the game of Snake. You plugged in 8 volts and you Sudoku'd, right? You finished your row by using Ohm's law. Then 90% of the time, although there are some exceptions, you will find yourself staying in the same column and figuring out a current about another part of the circuit. And so hence 0.5 amps. And we did that and we showed our work, right? Current, let's do a little color. Current, right, adds up in parallel. And you have to be pretty fluid with the formulas, and that's where a note card or a reference card would make a huge difference. Okay, so what I said is that we, anytime you have two pieces of given in a row, you can always finish your like a row. We're now on to R2, and specifically we're trying to find the V2, and V is equal to I times R. So we have a current of 0.5 amps times a resistance of 4 ohms, and we get V2 is 2 volts. There would be 2 volts dropped off here. Okay. Now, a lot of people say, but how do I label that? Well, if you want to show a voltage drop, I always make the tent over the top, and I write 2 volts here. Then look very carefully at some of the other information we originally had. We originally knew that there was 8 volts available, right? Think of it as energy available between the high side, the left, and the 0 side on the right. So if we've just lost 2 volts, and what we're going to do now is we're going to jump back in and show our steps. Now we know that in a series circuit, the voltage 1, the voltage drop, right, at resistor, actually let's do it at voltage 2, plus the voltage of the parallel portion has to be equal to the V total. And the reason for that is, right, series circuit, add up voltage. And so we put that in. We know that V2, we know that V2 is 2 volts. We don't know, plus the voltage parallel. Equals 8 volts. And I think that's actually pretty easy to spot, even without a calculator. You have 6 volts remaining. And that's going to be 6 volts for both resistors in parallel. And now it's a matter of finishing up where you just simply do one more Ohm's law. I equals V over R. 6 over 48 is an eighth, 0.125 amperes, and 6 over 16, or 3/8, is 0.375 amperes.